No, there's not. Yeah, no, I don't think, I mean, not in physics. I don't know, like you could check to see
Maybe there's like an
engineering, yeah, applied science or engineering, maybe they have something like that. I'm not saying that they do, that's something that might be worth checking. Yeah.
Yeah. Actually, got figured out how to they. I think each playing like so there's key speak on plus. There was I remember a lot of them. She was like 4 classes. It was awesome. To describe what it feels like, I couldn't describe. I couldn't tell you what it actually is. It's like I worked on a lot. I don't know. But she was a CHC in machine, so it was sex gun is messed up. Why doesn't it come? It's what did you they don't understand and they don't respond. Yeah, that's the reason why that is the reason why they swear. Are they? No, okay, no, I'm not gonna be dealt with that here. No, it is actually the reason why when we had we have one thing to add. The real piece like was probably also assuming with storage, you need squares pack nicer. Oh, that's no, what's like the line is not square or an X. No, I don't know why these squares. Yeah, like I'm sure the red does rise. I was gonna say that. My favorite. They call me a complex number. I'm assuming. I don't know what it was like. Yeah, he is like, yeah, thank you. Remember that word? He's like, had like a whole
Yes. Congratulations. What is it?
Yeah. Trying to see me Euler.
Most important applications you ever had.
Pretty much just. That's, dude, that's like.
That's the layman's way to describe.
My favorite thing to write.
Yeah, but he has the greatest constant ever. E to the x is a number where for any value of x, e to the x is equal to the slope of the tangent lines and the area from minus infinity up to x.
I like to think.
Pretty amazing.
Pretty good number.
And e is a irrational number, and it's also called a transcendental number.
Yeah, it's crazy. I had a. You remember? I struggled with take the integral of the black body equation. Oh, yeah. Right, and it ends up with a transcendental. I gave it to my math teacher. I was like, can you figure this out?
If you can actually solve.
Euler, Riemann did a bunch of stuff.
Letter of reality.
I mean, yeah, stuff. They're all pretty good.
E equals pi equals 3.
How like engineers will do this equals 3?
I saw on our last astronomy homework.
The word?
Was it the last astronomy homework? Or we had to go to this is with here. This is here.
I was doing that, I was like, I don't know what the radiation percentage respect the like surface area. I think you did, and then reverse it back. From like, from like a Earth.
I used 25. Yeah, me too.
That's smart. I just, yeah, I just sourced like surface area and then reverse back and was like, alright, well.
But if you would sign longer than the other,
Yeah,
it's not you. I know my things. Like after electric, he was showing us, I don't remember doing that. Jordan guys. Yeah, it had like interactive. I remember seeing.
So,
Aren't we all?
my big question, so how did Euler figure out which ones, was because you can take,
All right, so let's get started. The first thing I wanted to mention is today they released the final exam schedule. So ours is on December 12th. That's a couple days after the exam period starts, I think, 2 or 3 days. Unfortunately, it's an evening, so it's a 7 to 9:30 exam. But anyways, that's the time that they scheduled. The other thing I just wanted to highlight is we're gonna continue our discussion of complex numbers today, and there is, I'm sure many of you maybe are familiar with the Number File YouTube channel. They have a pretty nice video that introduces complex numbers, and so I encourage you to watch it. The video is actually for the so-called fundamental theorem of algebra, but the first 10 minutes is all an introduction to complex numbers. Okay, so let's see if I can get this thing back up. Let's go into full screen. All right, so what we were talking about is just like a math problem, right? We defined the square root of -1 to be this plus or minus j. And so far, the only thing we've done with it is we've been able to use it to help us write down results for the square root of a negative number. So if we started with this quadratic equation here and we plug it into the quadratic formula, it has part that is like the square root of b squared minus 4ac. And if your coefficients a, b, and c work out so that you have a negative under that square root, defining the square root of -1 as j allows us to find some solutions for x that we otherwise wouldn't be able to write down. So what I want to do today is I want to see if we could work out some properties of these complex numbers. So the first thing I'm going to say is that in general, we call the real part of a complex number. I'm going to write complex number as z equals x plus jy. So by the real part, we would say the real part of z is just equal to x. Okay, so it's anything in this expression that's not multiplied by the j. So anything in z that doesn't involve j. Okay, and then likewise, the imaginary part is all the stuff that does multiply a j. So it's going to be just the y. So when people say the imaginary part of complex number z, they don't mean j times y. It's just the coefficient that multiplies the j. So this is anything that multiplies j, but not including j. Okay, and so this is the real part of complex number z, and this is the imaginary part of z. All right, so what I'd like to do now is I'd like to see if we can come up with a way to visualize these complex numbers. And the way we're going to do it is let's just write down the number line for just our regular normal numbers, not complex numbers. So let's draw the number line. And so what we can do is we'll just draw over here. I'm going to give myself a bit of room, actually. I'll just draw an axis here, and somewhere on this axis is 0. And what I want to do is I just want to write down a bunch of our real numbers on this number line. So the integers are easy. So there's 1, here's 2, here's 3, here's 4, and of course this keeps going. And then off to the left, we have -1, -2, -3. So all of our integers live on this number line. We could also start trying to find fractions. So 1/2 lives over here. Here's -3/4 somewhere over here. And you could put all your fractions in there, like 5/3 or whatever you have. You could even put in like some irrational numbers. So numbers that where you can't express them as a fraction of 2 whole numbers. So √2 is 1.41. So √2 sits somewhere over here. So there's even our irrational numbers. We could find our transcendental numbers like pi. So for example, -pi would sit over here somewhere. And e is 2.7 something, it sits over here. So all of the numbers that we know and love live on our number line. But now we have a problem. We have one of our solutions to our quadratic equation from last time is, well, what about numbers like 1 plus or minus j root 3. These don't fit on our number line. And so what we're going to try to do is we're going to try to generalize this. So instead of having a single axis of only the real numbers, we're going to add a second axis perpendicular to the first one, and we're going to call that our imaginary axis. So to extend this picture, we're going to create a second axis that's perpendicular to the first. So we'll call the original axis the real axis, and the new perpendicular axis, the imaginary axis. Okay, so let's do that. So I'm gonna insert my new axis over here. And now I'm gonna call this the imaginary axis, and this one is gonna be the real axis. So I can start putting some divisions on my imaginary axis, and I can start saying, well, if I had a purely imaginary number, maybe like, I don't know, j times root 3, the imaginary component of our solution would be the root 3. Well, actually, let's not start with root 3. Let's just say that I've got the imaginary number j, would sit right here on this imaginary axis. And then this one would be 2j. And we'd have 3j. And then, of course, we could have minus j, minus 2j, minus 3j. Okay. And then in general, we have numbers like this that have both real and imaginary components. So we could find a number like, I don't know, let's make it easy first. Let's place z equals 2 plus 3j on our new coordinate system. Okay, so all we would do is we'd go 1, 2 spots along the real axis, and then we'd go 1, 2, 3 on the imaginary axis, and this point here would be z is equal to 2 plus 3j. Okay, so now we have all this kind of new landscape to play with. Does this remind you of anything? If you had like, what does this sort of plot remind you of? Yeah, it's a Cartesian coordinate system in 2 dimensions. In fact, even the way we write down our complex number, 2 plus 3j, I mean, it looks like a 2-component vector. And so a lot of the properties that we already know from 2D Cartesian coordinate systems, particularly polar coordinates, are going to transfer into how we handle our complex numbers. So notice that in many ways, z equals, say, x plus jy, where x is going to be the real part and y the imaginary part of our complex number z, is similar to a 2-component vector. I don't know, let's say v is equal to x times I hat plus y times j hat. So what I'm going to do is I'm going to draw two coordinate systems. One will be the real and imaginary axis for our complex numbers, and then one will be an x and y axis for our 2D vectors. So we'll have our imaginary axis here, and we'll have our real axis here. I made that a bit big. I want to have two side-by-side plots. Here's our real axis. Okay, and then over here will be our XY coordinate system. Okay, so let's imagine that we have a complex number z equals x plus jy. And so what we would do is we would say, okay, we go along our real axis until we find the point x. And then we go along our imaginary axis until we find, say, j times y. And we can go and join those two. And this is the point z equals x plus jy. And so here's our vector x times I hat plus y times j hat. And so now I drew my coordinate system in a stupid way. X should be the horizontal axis and y the vertical axis. Okay, so same thing, we just go out here until we find the point x, and we go over here until we find the point y. And this corresponds to the point xy. Okay. So for our usual Cartesian coordinates in 2 dimensions, is there another way that I could represent this 2-dimensional vector? What's another way? Yeah.
A magnitude.
Yeah, what? So a magnitude and what? A magnitude and a direction or an orientation. So what I could do is I could say, well, another way of representing this 2-dimensional vector is by specifying a length or a magnitude. So this is the length of v. And then I have to specify an angle. I'm going to use phi. And there's an angle phi measured from the x-axis. And so what I could do is I could say, well, then v is equal to some magnitude or some length, and then the direction is phi radians rotated counterclockwise from the x-axis. That's a bit of a mouthful, but that's what I could do. And these two representations have all of the same information. And in fact, if I do that, I could even go between these two representations, because if this is length v, and this is the x is the side that's adjacent to the angle phi, I could write that x is just the magnitude of the vector times cos of phi. And likewise, I could say this height y is the magnitude of this vector times the sine of phi to give us the opposite side, the length of the opposite side. And so y is likewise the magnitude of vector v times sine of phi. Well, there's nothing stopping us from doing the same thing for our complex number. What I could do is I could say, well, what I might do is instead of giving the values of x and y, I can say my complex number is a certain distance, the magnitude of z, away from the origin, and then it's rotated a certain amount away from the real axis. And so I can say this is the magnitude of z, and we're going to rotate counterclockwise an amount phi from the real axis. Okay, so we could likewise represent complex number z as a distance from the origin, which I'll denote z, and that's called the magnitude of z, and an angle phi counterclockwise. Let's say angle phi may be measured counterclockwise from the real axis. And all of this stuff is also true. Like if I can look at x here, and I can say, well, that's just the magnitude of z times the cosine of phi. So x is going to be the magnitude of z times cos of phi, and y will be the length of the opposite side, which is magnitude of z times sine of phi. All right. So if that's true, then what I could do is I can put these expressions 1 and 2 back in here. And so let's call this number sign, because I've already used 1 or 2. So let's plug 1 and 2 into number sign. So number sign just said that our complex number was equal to x plus jy. But now we've said x is the magnitude of z times cos of phi plus, let's see, j times the magnitude of z times sine of phi for y. And so I could factor out that common factor of the magnitude of z. This is cos phi plus j sine of phi. And so it looks like already we've come up with 2 ways to represent the same complex number. One way is just to specify the real and imaginary components, and then the other way is to specify a magnitude and an angle phi rotated away from the real axis. And so these are 2 equivalent ways of representing the same complex number. Okay. What if I wanted to go between these 2 representations? Well, what we might do is consider, well, let's go back to this. How would I, if I started by giving you the components of a 2D vector, x and y, how would I find the length of that vector? Yeah, it's just a right angle triangle, right? How do I find the length of a hypotenuse of a right angle triangle? Pythagoras theorem. So what's Pythagoras theorem? Yeah. Right, x squared plus y squared. So let's see if we can extend this kind of analogy a little bit further. So we'll go back, and so let's consider x squared plus y squared for our complex number z. Okay, well, from equation 1, x squared is going to be the magnitude of z times cos squared phi. Right? So I just squared this thing, and y squared is magnitude of z squared times sine squared phi. And so 2 y squared is going to be z squared times sine squared phi. And so if I add these two up, they're going to have a common factor of z squared. So x squared plus y squared is going to be z squared. And then what do we have? We have from the x squared, we get cos squared. And from the y squared, we get sine squared. But of course, cos squared plus sine squared is just equal to 1. And so therefore, the magnitude of our complex number, or if you like the length, when we plot it on this type of graph, is just given by the real part squared plus the imaginary part squared, and then take the square root of all of that. This plot here, this plot is called the complex plane. This set of coordinate systems is called the complex plane. So along the real axis, all your numbers are purely real. That's just the number line that we wrote down right at the beginning. Along the vertical axis or the imaginary axis, your numbers are purely imaginary. And then anywhere else, you have real and imaginary components. Okay, so this is also equivalent to x is just the real part of complex number z. And then we have to square it. And then y is just the imaginary part, the imaginary component. All right. So that's the magnitude of z expressed in terms of x and y. What if I wanted to get the, let's see, am I going to find that? Where is it? All right, here we go. What if I wanted to have an expression for phi in terms of x and y, right? I want to eliminate the magnitude of z here. What could I do with equations 1 and 2? How would I eliminate z from 1 and 2? Right, I could solve for z here, like I could say z is x divided by cos phi, and then I put that in here, or I could just take the ratio of these two. If I take their ratio, say y divided by x, what will I get? That's right. So taking the ratio, y divided by x is equal to the magnitude of z sine of phi divided by the magnitude of z cos of phi. That's going to cancel these things, and so we get tan of phi. So therefore, the tan of this angle is going to be equal to y over x, which is the same thing as the imaginary part of our complex number divided by the real part. And so what we've done so far is we've come up with two ways to represent a complex number. And we can switch back and forth between those two methods. Yeah.
Supposed to be a
Oh, yeah, down here. Yeah, you're right. Thank you. Good. So let's summarize what we've seen so far. Let's call it summary. So we can represent any complex number z in two ways. So we could say z is equal to x plus jy, or we can say z is equal to the magnitude of z times cos of phi plus j sine of phi. If you're given x and y, you can find the magnitude and the angle phi using the following. So if we're given x and y, we can say the magnitude of z is x squared plus y squared square root, and the tan of this angle phi is y over x. Now, you might be given the other information. You might be given the magnitude and this angle phi, which is usually called the phase. So if you're given those two bits of information, you can also find x and y. So if we're given the magnitude and phi, then we could write x is the magnitude times cos phi, and y is the magnitude times sine of phi. So those are our two representations and the way that we can switch between the two. Okay, so that's sort of the starting point. And let's see, is there anything else I wanted to say before? No, so that's good. Okay. So what I want to do next is, so far this is just a definition in terms of like, a mathematical definition and kind of working out some of the manipulations we can do. So far, we haven't applied this to electronics at all, and that will take a class or two before we get there. What I want to do is I want to do a little bit more working out some of the properties of the complex numbers. And to do that, we need to use a Taylor series. Now, I know you already told me that you've seen Taylor series. I'm just going to do a quick little review so that we are all on the same page when we do this next little manipulation. Okay, so let's do a review of Taylor series. In fact, does anyone know who remembers what's it called when you do a Taylor series expansion about, say, x equals 0? It's the Maclaurin series. So what I'm really going to do is the Maclaurin series. And I don't know how to spell Maclaurin series. I don't know if that's how you spell it. It's probably wrong. Okay, so here's the claim. So the claim is that we can express any function that is infinitely differentiable as a power series. Okay, so I have some function. It could, as long as I can take derivatives of it over and over again, I'm claiming that I could write this as a power series or a polynomial, like so. And this would go on for infinity. And our job is, if I want to justify this claim, our job is to find the values of these coefficients, A0, A1, A2, and so on. So we need a scheme for finding the values of the coefficients A0, A1, A2, and so on. Okay, so how are we going to do that? Well, finding the first one is easy. So let's consider this function evaluated at x equals 0. Okay, so what I mean by this is just take our function f of x and sub everywhere you see an x, replace that with 0. Okay. So if I do that for this kind of conjecture that we can write this as a polynomial, I put 0 here, here, and here for x and x squared and x cubed. And I'm going to get a0 plus a1 times 0 plus a2 times 0 plus and so on. Everything that multiplies some power of x is going to vanish. And all we're going to be left with is a0. And so therefore, a0 is just equal to f evaluated at 0. All right, so that's 1 down. There's only an infinite number more to go. All right. Does anyone have an idea what's the next? How are we going to find the a1? I want to do the same trick. I want to be able to sub in 0 and have only the a1 survive. How do I get rid of a factor of x? Take a derivative. So let's try that. So let's next consider df by dx. Okay, so df of dx is going to be the derivative of this power series or this polynomial. So the first term is a constant, and so when I take its derivative, I get 0. And then the next one is a1 times x. If I take its derivative, I just get a1. Then I have a2 times x squared. When I take its derivative, I get 2 a2 times x. And then I'm going to get 3 a3 times x squared. And this will just keep going. So you could probably see already that if I now take this derivative and evaluate it at x equals 0, the only thing that's going to be left is a1. And so therefore we could say a1 is going to be df dx evaluated when x equals 0. That's our next coefficient. We'll do one more. So one more is we're going to consider the second derivative of f with respect to x. Okay, so d2 f dx2 is equal to, well, I have the first derivative written down here, so now I just take another derivative of this thing. A1's a constant, take derivative, it's 0. Then I have 2 times a2 times x. When I take its derivative, I'm going to get 2 a2. And then when I take the derivative of the next term, 3a3 x squared, I'm going to get 3 times 2. And I'm going to write it as 3 times 2 instead of 6, times a3 times x, and plus so on, right? The next one is going to be, if I wrote down the next term, it would be 4 times 3 times a4 times x squared. Okay, so then let's see. If I want a2, that's going to be d2f dx2 evaluated at x equals 0. Almost. This would give me 2 times a2. So what I have to do is I have to, include that factor of 1/2. So continuing in this fashion, we would find, well, let's see. Let's just do it in our head. If I took a third derivative, I'm going to get 0 plus 0 plus 0. plus 3 times 2 times a3, and then I'll have a 4 times 3 times 2 times a4 times x, and so on. And if I put in 0 for x, what I'm going to find is that a3 is going to be 1 over 3 times 2 d2, d3 f dx3 evaluated at x0. And you could probably see the pattern. Instead of writing 3 times 2, what's a better way of writing that? 1 over 3 factorial d2f. Sorry, I keep putting 2, it's d3. So in general, the nth coefficient is 1 over n factorial, the nth derivative of our function with respect to x, evaluated at x equals 0. Okay, so that means we can write our Maclaurin series in the following way. Therefore, I'm going to write this, I'm going to say the Taylor series expansion of f of x about x equals 0 is then, okay, so it's f of x is the sum of n equals 0 to infinity 1 over n factorial times the nth derivative with respect to x evaluated at x equals 0. This whole thing is the coefficients, the a values, an, and then we multiply by x to the power n. And that's our Maclaurin series. Okay. So far, I haven't told you why we're doing this. Let's start working out some examples. The reason we're doing this, I'll give you a hint, is that if we go back to our complex numbers, we have cosine and sine functions related to our complex numbers. So what I want to do is I want to write out Taylor series expansions for those cosine and sine functions and see where it leads us. Okay, and we have 10 minutes, so let's see how far we can get. So let's do an example. Find the Taylor series for sine of x. Remember, the only condition was that we had to be able to differentiate our function repeatedly. And I can do that with sine x. Because the first derivative is just going to give us cosine. Then I take a second derivative, I get minus sine. So we just keep switching between sines and cosines, and we never run into trouble. Okay, so we're going to construct this table. All right, so we'll start with n equals 0, and that is going to correspond to our a0 coefficient. The 0th derivative of sine x is just sine x, right? Don't take a derivative. That's what the 0th derivative tells us. And then we're going to do sine x evaluated at x equals 0. Well, that's just 0. What's 0 factorial? 1. Okay, so we don't have a problem with 0 divided by 0. Okay, good. So apparently our first coefficient is 0 for the sine function. Okay, then we go n equals 1. That's going to give us the a1 coefficient. The first derivative of sine is cos. So we get cos x. Cos x evaluated at 0 is a 1. And then 1 divided by 1 factorial is still just 1. Okay, so our second coefficient is a 1. 2. A2. So the derivative of cos is minus sine of x. And then when I put in x equals 0, I'm going to get 0. And maybe you can see already that the sine function is going to have 0 for all coefficients that are even. So including a0. So it'd be a2, a4, a6, a8. They're all going to be 0 because we're going to end up with either sine x or minus sine x, and then evaluated at x equals 0, that's going to vanish. So we can see that all even values of n result in an equals 0. All right. That maybe should make you feel good because the even values of n are the even powers of x, and sine's an odd function. So why would it have the even powers of x, which would give you even type behavior, even functions? Okay, anyways, let's go to 3. So we want to find the a3 coefficient. So we have to take the derivative of minus sine x. That's going to be minus cos x. And let's see, minus cos x at x equals 0 is minus 1. So we're going to get a minus 1 here. And then we have to divide by n factorial. So we divide by 3 factorial. Or divide by 6. If we did the fourth one, the derivative of minus sine x, minus cos x is going to be sine x. Now we're back where we were. We're going to get 0. If we do the fifth one, we're going to get cos x. Cos x evaluated at x equals 0 is plus 1. And we have to divide by n factorial. So we divide by 5 factorial. Factorials blow up really quickly. So 3 factorial is 6. What's 5 factorial? 120, yeah. So they get really big really fast. Okay, and so this would continue on. So not only are the even coefficients all 0, the odd ones alternate in sign. So we go from plus 1 to minus 1 over 3 factorial to plus 1 over 5 factorial and so on. And the result that you get is sine x is approximately x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th plus 1 over 9 factorial x to the 9th minus and so on. I put approximately. It's exact if you keep an infinite number of terms, but of course that's not practical to do. So at some point you truncate the series. It's safe enough to truncate as long as you go to high enough term, because you're going to end up dividing by a huge number, or equivalently, the an coefficients get really small. Okay, so exercise for the student. Exercise for the student. Show that the Taylor series expansions for cos x and e to the x are given by. Okay, so cos x, it's like the sine x expansion. It's going to have alternating signs, but it's going to be all the even powers because cos is an even function. And it turns out to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial plus and so on. And e to the x, it turns out that it has all the powers of x, and the sign is always positive. So if you just go through the same routine that we just did for sine of x, you can show that e to the x and cos x are given by these expansions. Okay, so why bother doing all of this? So what I want to do is the following. So to connect the Taylor series of, let's say to connect Taylor series to complex numbers, let's consider e to the j phi. i.e., what we're going to do is we're going to sub x equals j phi into the Taylor series of e to the x. So let's give it a try. Let's see what that would look like. I'm just going to write down this series again, but wherever I see x, I'm going to put j times phi. Okay, so e to the x is e to the j phi is equal to, well, 1, nothing happens there. And then I have plus x. X is j phi. And then I have plus x squared, j phi squared, divided by 2 factorial, plus x cubed, j phi cubed, divided by 3 factorial. I need to keep enough so that we can see the pattern. And I'll go up to n equals 5. And so it'd be plus a bunch of other stuff. Okay, so e to the j phi is equal to, well, let's see. I can't do anything with these first 2 terms. It's just 1 plus j phi. But now what I'm going to do is I'm going to make a table here, and we'll do n, and then we'll do j to the n. So let's start with 2, 3, 4, 5, 6, and so on. J squared, which j squared equal to? -1. Okay, so here I have j squared times phi squared, but that's minus phi squared. So this is minus phi squared over 2 factorial. Well, j cubed is just j times j squared, but j squared is -1, and so that's minus j. Okay, so over here, I have j cubed is the same thing as minus j. So we have minus j phi cubed over 3 factorial. Okay, j to the 4th. That's just j times j cubed. But j cubed is minus j. So if I multiply by j, we get minus j squared. What's that? Plus 1. Okay, so we're going to get plus phi to the 4th over 4 factorial. We'll do one more. J to the 5th is j to the 4th times j. But j to the 4th is 1, and so j to the 5th is just j, plus j phi to the 5th over 5 factorial. And then there's going to be some more stuff. In fact, the next one would end up being negative. Okay. Well, I'm going to stop in just 1 minute here. Notice that I've got some terms that have j, and then I've got terms that don't have j. So what I'm going to do is I'm going to rewrite our e to the j Taylor series, where I'll keep all of the terms that don't have j, and I'll group them together. So it'll be 1 minus phi squared over 2 factorial plus phi to the 4th over 4 factorial. If I kept the more, I'd have minus phi to the 6 over 6 factorial, plus and so on. And then I have a bunch of terms that do have j. So I have j times phi. So I'll get phi here. And then I have minus j times phi cubed over 3 factorial. So we get minus phi cubed over 3 factorial. Then we're going to get plus phi to the 5th over 5 factorial, minus and so on. What is this thing in the first bracket? It's a real number, but it's exactly equal to our cosine Taylor series. Oh shit. Okay, so cos phi. And this one here is exactly the sine series. And this is Euler's equation. Euler's equation is e to the j phi is equal to cos phi plus j times sine of phi. Okay, and that's where we'll pick it up next time. And this is going to be really fundamental to how we use complex numbers to analyze problems in electronics. Okay, good. So thank you very much. We'll see you on Wednesday. Oh, yeah, well, I've got a. Sure, yeah. Yeah, we could give it a try, yeah.